So it has been a lot of work, a lot of exciting work to prepare this conference. So let me personally thank everybody in the team, because it was really a good time to spend for the community. And I would like to personally thank again all who has contributed and the plenary speakers for the first. It's an honor and a pleasure to introduce Director Martin Milton and to present him as an outstanding personality in our community. Dr. Martin Milton received a BA in physics from Oxford University in 1981 and a PhD in laser physics from Southampton University in 1990, followed by an MBA from the London Business School in 1991. Dr. Milton joined the BIPM in October 2012 as Director Designate and became Director on the 1st of January in 2013. Before his move to the BIPM, Dr. Milton spent 31 years at the National Physical Laboratory, NPL, United Kingdom, where he was a fellow in the Analytical Science Division. As Director of the BIPM, he now manages 74 staff and oversees the impact of the program of work and relations with stakeholders, including principally the 60 members states and the 42 associate states. Dr. Milton has published more than 90 papers in peer-reviewed journals and has received several awards, including most recently the Finkelstein Medal of the Institute of Measurement and Control for notable contributions to measurement internationally. So it's an honor to introduce the talk of Director Milton, the new definitions of the base units of SI, using the rules of nature to create the rules of measurement.
Thank you very much, Davide, for that very kind introduction, and thank you to the organisers of the conferences for your invitation. It's a great pleasure to be here. Over the last few years, me and my colleagues and members of the CIPM and directors of NMIs around the world have seemed to be presenting an inordinate number of talks about mass and about electricity, because we've devoted a lot of our time to promoting the importance and explaining the benefits of work that was being done to redefine the base units of the SI. That work came to a conclusion in November last year, and I think there's a great symbolism in being here today, because I'll talk about the work that led up to changes agreed last November, but of course we look now to the future where perhaps we will no longer be talking always about mass and electricity, but perhaps we'll be talking about new challenges for measurement science, such as moving towards an optical definition of the second. And I'll say a little bit about that at the end of my talk. So I'd like to say something about the history to set the background for the metric system and the signature of the Metre Convention, talk about the work that led to the redefinition of the SI last year, talk about implementing those definitions, and then say just a few words about moving towards a new definition for the second. So, why was the metric system of so much interest? The metric system, of course, was first introduced after the French Revolution to allow fair trade by weight and length. And for those of you, those of us who spend your time trying to explain to people the importance of accurate measurement, you should understand that at the time of the revolution, at the end of the 18th century in France, it was the people who came forward with one of their major complaints was that they demanded access to a fair system of measurement. Wouldn't it be easier for us all if the people rose up today in our society and demanded access to a fair system of measurement? Well, perhaps we're doing a better job in delivering it already. So following the revolution, the eminent scientists of the period came together and came up with proposals based on work that had been done in France throughout the 18th century to define the metre based as 1/10,000,000th part of the arc of the meridian through Paris, of course, and then the kilogram, subsidiary to the metre, as being the mass of 1 litre of water at its temperature of maximum density. The savants and the academicians brought a proposal to the National Assembly in 1799 in which they proposed the system based on these definitions of the metre and the kilogram, and that they proposed that this would be a system that would be for all people for all time, à tous les peuples, à tous les temps. But in 1812, and perhaps less promoted in the history of the metric system, Napoleon abandoned the system for various reasons, perhaps because he thought it was too much of a complicated technical thing when he had bigger ambitions. But in 1837, the metric system was reintroduced in France by the law of 1837, and at that time a medal was printed with the famous phrase à tous les temps, à tous les peuples, the first time that we see that medal actually struck, something they promised to do in 1799 but never achieved at that time. But here in 1837, the medal was struck, proclaiming the metric system for all times, for all people. But confusion developed through the 19th century about what truly were the definitions of the metre and kilogram. Were they the old revolutionary standards, the definition according to the quadrant and according to the density of water, or were they the artifact standards that have been put in place as a practical way to realise those definitions? And moving into the period of global industrialisation, there were new demands for accurate measurements. On one side, there was increasing demand for accurate measurements of length, for mapping, perhaps for the worst reason to know how far, to calculate how far a cannon can be fired, but also for matters of property ownership and distance travelled. And then on the other side, this was the period of the great exhibitions, initially in London and then in Paris, where the manufacturers of the world came together. And part of what they did at those exhibitions was to compete for prizes for the best performing equipment. And it became clear amongst the panels judging those competitions that it wasn't possible to make fair comparisons about the performance of this industrial manufacturing equipment because there wasn't a common understanding of how to measure length and mass. So in 1875, 17 nations came together in France to sign what we call the Metre Convention. Now, in fact, it's as truly called the Convention to assure the international unification and perfection of the metric system. Now, what we call the Metre Convention. So the Metre Convention established an international organisation, the BIPM, under the authority of the General Conference of Weights and Measures, the meeting of the member states. And the member states would elect the International Committee, now 18 members elected from different nationalities. And the CIPM would supervise the work of the organisation, including the staff and including myself and our facilities and the meetings that take place where we're based. The CIPM have also set up, very importantly, their 10 consultative committees, which play the leading coordinating role in the 9 areas of metrology as we look at it today, together with the overarching work on units by the CCU, the Consultative Committee on Units. The work of the organisation has greatly increased since 1875. At the end of last year, we had 59 member states and 42 associates. So we can talk about having 110 of the 193 states of the UN participating. Even now, we have states joining. Montenegro and Ukraine became member states last year. So let's say something more specific about the SI. When I talk about the SI to wide audiences, I know that from the perspective of those of us working in measurement science, we immediately think about the base units and the derived units. But you know, I think when we talk to our fellow citizens about the SI, perhaps they more often think about the prefixes. They think about micro and kilo and mega, these being the things that tell people you're using SI units. So we have a system that encompasses these three different elements, the base units, the derived units, and the prefixes, and yet they have huge impact in everyday life. So our system of 7 base units, there's no great significance in the fact that there are 7. It turns out to have been a convenient development to have 7. One could have fewer, one could even have more. The great British chemist Edward Guggenheim said, if you give me the man who uses fewer units and the man who uses more units, I prefer the man who uses more units because he will be easier to understand. So yes, we could pare this thing right down, but we then produce a system that could be very difficult to understand. So here are our 7 base units. I'll not need to read them all. And until November last year, 3 of those were based on what one can reasonably call fundamental or conventional constants. So the metre, of course, defined with respect to the speed of light, the ampere with respect to the permeability of free space mu0, and the candela defined with respect to what we have to call a conventional technical constant, KCD. 3 were based on atomic or material properties. The second, of course, on the hyperfine splitting in cesium, the Kelvin on the triple point of pure water, and the mole on the mass, on the amount of substance contained within 12 grams of pure carbon-12. But just one stood out, the kilogram, as being based specifically on an artifact. But there are some limitations established in this system which really motivated the changes that went through last November. The ampere hasn't been realised by its true SI definition since at least 1990, when the electrical community agreed a convention that they would base their definition of the volt and the ohm on the 2 quantum electrical effects. So the electrical community, if you like, had been operating outside the SI since 1990. The Kelvin, again, by convention, primary measurements of temperature weren't referred to in particular, but the practical measurements of temperature were made with respect to the accepted international temperature scale, ITS 90, making only passing reference to the definition of the Kelvin. The kilogram was based on an artifact. The nature of the artifact is one could never be certain that it was stable. I don't think actually for me there was ever any convincing evidence that it wasn't stable, but nevertheless we couldn't prove either that it was stable. And then the mole. The mole, if you're familiar with discussions in the field of chemistry, although there's no problem with the realization of the mole in terms of uncertainties or anything in chemical measurement, there has certainly been problems with teaching and understanding the mole, and there was an opportunity to bring forward a definition that would better reflect the way chemists think about measurements in chemistry. So the proposals to make the changes, I'll introduce the changes in a moment, were agreed at the 26th General Conference held in November in Versailles last year. 59 states came together and agreed on these 5 resolutions. I'll say something about the revision of the SI, that's Resolution A, and at the end of my talk I'll say something also about Resolution B on the definition of timescales. So the 7 base units now, we have 4 new definitions, and these 4 new definitions give us the opportunity to link the definitions of the base units to our fundamental principles of physics, to our best understanding of the way the world, the way nature works. So we've been able to link the kilogram to the Planck constant. I'll explain how that's done. The ampere to the charge on the electron, the Kelvin to the Boltzmann constant, and the mole to the Avogadro constant. So bringing back the existing definitions of the meter and the candela, which were already linked to constants, leaves just one of the definitions, the second, that makes any specific reference to the property of a system such as an atom. So there are the new definitions, and between the new definitions there are different linkages than there were before. The definitions don't stand on their own, except for the definition of the mole, which is uniquely linked to the Avogadro constant. All you need is the Avogadro constant to realise the mole, but the others are interlinked. So how do we implement this? Well, let us start by saying a little bit about the ampere. So the old definition of the ampere, my best understanding and best way to explain it was that the ampere simply told us, the definition of the ampere simply told us how to write Ampere's law in the form there. I won't read the definition, but the definition of the ampere told us that when we write Ampere's law in this way, the proportionality constant there is mu0. And of course, from Ampere's law, we can define Coulomb's law because we know the relationship between mu0 and E0. But in practice, as I said, since 1990, the macroscopic quantum effects have been the basis for the reproduction of the electrical units, based for the voltage from the Josephson effect, defined by 2E over H, and the quantum Hall effect, defined by H over E squared. And in 1990, the electrical community agreed that they did not wish to be any longer subject to uncertainty due to the best knowledge of E and H, and they would therefore choose conventional values for E and H, giving these values for Kj and Rk. But it was a convention outside the SI. In other words, these values aren't consistent with the value of mu0, which is exactly 4 pi times 10 to the minus 7. So the new definition works the other way around. We just say that the ampere is defined by taking the fixed numerical value of the elementary charge, to be that number, when expressed in the unit coulombs. But how does it work in practice? Well, since we have a system now in which H is fixed by the definition of the kilogram and E is fixed by the definition of the ampere, then both 2E over H and H over E squared are fixed, and we can realise the voltage and the quantum Hall effect with no uncertainty due to the definitions directly with respect to those fixed constants. But a consequence of the work done to determine the best values for E and H is that the new worldwide agreed values for E and H differ by a small amount from the conventional values adopted in 1990, such that when the changes come fully into place on the 20th of May this year, there will be a small shift in voltage measurements there of 10 parts in 10 to the 8, and a small change in impedance measurements by 18 parts in 10 to the 9. The change in impedance measurements is certainly insignificant. The change in voltage measurements may have some significance, certainly for NMIs working at the highest level, but also possibly for some industrial and calibration companies working at the very highest level, the sort of organisations that are in very close contact with their NMIs, of course. So we need now a way to link electrical units to mechanical units, to link the kilogram to the ampere. And this is of course, the moving coil Watt balance, now named the Kibble balance after Brian Kibble, its inventor. So the Kibble balance is one of those wonderful bits of physics that one hopes in the future will even be taught at schools, because it has that sort of quality in the bits of physics that we probably all most enjoy, that the more you look at it, there's slightly more depth in it than one thought before. So it's a two-phase experiment, and in the first phase we invoke Ampere's law to weigh a mass with a force mg against gravity against a magnetic field, or against a current times rate of change of flux. So we have the equation mg equals ILB. In the second phase, we take exactly the same balance, except we take the mass off the right-hand side, we insert there a motor, and we move the coil. So we move the coil, we induce a potential, and according to Faraday's law, the potential is minus the rate of change of flux linkage. So we can write that equation as U equals BLV. So taking those two equations, we can now cancel B and L and end up with this magnificent equation UI equals mgv, which very simply we see sets electrical power equal to mechanical power. It couldn't be more simple, but there's a great subtlety in the way the Kibble balance works, because it's an instrument, it's an experiment that sets equal mechanical and electrical power, but it does this without realizing power. There is no actual power in the system. There is only what you might call a virtual power. Consequence of that is that we don't need reference to the magnetic field, we don't need reference to the charge of the electron E, and neither do we need any reference to any inefficiency in the balance system itself. So if we assume the exactness of the formulae for Kj and Rk, which we're going to use to realise the voltage and the current, then we have the quantum version, if you like, of the Kibble balance equation, mgv equals h over 4 times 2 frequencies. So there we go. On the left is a reference to what was formerly the international prototype of the kilogram, and on the right there's a reference to h. So whereas in the past h carried some uncertainty with it, and there's been a trajectory on the uncertainty of h, most recently it's now 2 parts in 10 to the 8. Fixing that uncertainty enables us now to determine the mass of an artifact kilogram, m on the left. So here's our definition for the kilogram. It's defined by taking the fixed numerical value of the Planck constant to be h, equal to that value when expressed in the unit joule per second. So how do we do this in practice? Well, in practice, we could use a Kibble balance, or we could use the silicon XRCD experiment, which is another experiment, another very elegant experiment that links the number of atoms in a sphere of silicon to the mass of that sphere of silicon. And since we can express the mass of an atom of silicon in terms of the mass of an electron, and since we can link the mass of the electron through the Rydberg constant to the Planck constant, we can make again the link between mass and the Planck constant using the silicon experiment. Where I said something about the consequences of introducing the change in electricity. The consequences of introducing these changes in the kilogram are probably a little bit more far-reaching amongst NMIs working at the highest level. The CCM, the Consultative Committee for Mass, is working on a protocol which is now at a very advanced stage, which will explain what is expected in terms of comparisons between NMIs that are going to realise these measurements at the primary level in order for those NMIs to gain traceability to their own primary realisations. So what do the mass community get out of this after having dealt with the complexity of these new primary experiments? Well, apart from being able to say that the world of mass is linked to the world of quantum physics, to make a real example of the advantages, in the field of mass, because we've worked for all of these years around a primary definition at the level of 1 kilogram, it's been necessary to set in place systems to make measurements at masses much lower than 1 kilogram and at masses much larger than 1 kilogram. These are very well-established processes, somewhat time-consuming, mass metrologists will tell you. But a consequence of them is that they spread the uncertainty over the system of mass measurements. So we look at the chart on the right there. If you follow the projected uncertainty based on having to subdivide the kilogram, if you get down to a nanogram, you end up with an uncertainty of close to 100%. Now, whilst one wouldn't make a case for the pressing demand to be able to make measurements at 1 nanogram expressed accurately in SI kilograms to some enormous level of uncertainty, I think one could accept that we would want a definition that did better than having 100% uncertainty at 1 nanogram. So there is much opportunity now in the mass field to be able to make measurements away from 1 kilogram, the historic starting point. So one can say the same about the Kelvin. I'll skip through that at the moment. So we now have a system which is based on fundamental constants. Many of our colleagues like to emphasize this. NIST were the first to produce a business card with all of the SI constants on. I think a number of NMIs have been giving these out. And of course, you can say to your friends, you can give them a business card like this, and you can say to your friends, there you go, you have everything you need to know for the SI. But what the NIST card and all of the other cards don't have is something printed on the back, which is that the consequence of the steps to make, to fix 4 fundamental constants, or to fix the numerical value of 4 fundamental constants. Of course, we now have a system with 4 unexpected variables. Fortunately, they're variables in parts of the system that most of our community won't be overly concerned with. But for the record, one should be clear that now MK at the top there, the mass of the international prototype, is an experimental variable with an uncertainty of 1 part in 10 to the 8. mu0 is no longer exactly equal to 4 pi times 10 to the minus 7. It has an uncertainty there of 2 parts in 10 to the 8. The temperature of the triple point of water has an uncertainty around a part per million. And the mass, the molar mass of carbon-12 also has an uncertainty. Again, of little significance to practical measurements in chemistry, but of great significance when it comes to teaching the principle of the mole the right way round. So, a question, why does this quantum SI that's been discussed so much depend on very complicated mechanical experiments? In fact, in Nature in 2012, they ran a piece on frontier experiments, tough science, 5 experiments as hard as finding the Higgs. And they listed in there the Kibble balance. So why is it we have to do something that is not quite as difficult as discovering the Higgs, but nevertheless pretty difficult, in order to realize this quantum SI? Why do we need a mechanical experiment? Well, if one thinks about it, the kilogram is intrinsically a macroscopic thing. It's stuck at 1 kilogram, and one can't do anything quantum with something as big as a kilogram. You're going to have to do a mechanical experiment. A second point is that the previous definition of the ampere, again, was intrinsically mechanical. It talked about the force between 2 wires. So if one was ever going to do an experiment that was going to be traceable back to the old definition in order to implement a new definition, one would have to do a mechanical experiment. So there we are. Inevitably, to implement this quantum SI, we're going to have to do a mechanical experiment. But why such a complex experiment? Well, here's the formula we like, that the mechanical power is equal to the Planck constant over 4 times 2 frequencies. Well, it turns out that we will need to do an experiment that has 2 phases in it. And the reason for that is that, one way to explain that, is that when you set up any sort of coil in a field, you want to avoid ever having to measure the field. So you're going to have to do something to cancel out the field in the equation, the way I said. So I suggest that it's inevitable that this mechanical experiment, which we think we have to have because the kilogram is mechanical, is going to need 2 phases to cancel out the bit of the electrical part of the experiment that we don't want to have to deal with. So here we are implementing our quantum SI, and yes, it has needed a mechanical experiment, but the field is now open to implement these definitions in new ways. So how far have we come? Here's a very brief history of the SI. It was initiated in 1960 with 6 units. In 1967, we had a new definition of the second. In 1972, we introduced the mole. We had a change to the candela. We introduced the speed of light to define the meter in 1983. And then in 1990, we set the thing back a little bit by introducing the electrical convention, the 1990 convention for the electrical units. But how far are we towards this atomic or quantum SI that really we like to talk about? Well, 2 years ago at BIPM, we had a workshop and we looked at the date we were operating in, 2017, and we discovered it was 50 years since the first paper that we could find that really talked about quantum metrology. This is a paper published in 1967 there by somebody called Barry Taylor, who many of you will know from NIST, although this was before Barry Taylor joined NIST. This is when he was at the RCA laboratories. And he first proposed using the Josephson effect as a standard to measure his voltage cells. So there we go, 50 years since the development of quantum metrology. And then in 1980, quantum metrology had a second leg to stand on, which was the quantum Hall effect, with von Klitzing's paper, very rapidly adopted by the NMIs as a standard for impedance. In 1990, the electrical community couldn't resist it any longer. They moved over to their quantum system. And in 2018, we brought them back into our system. But I said little about the event of 1967, because 1967 is probably the point when our SI truly started to become an atomic system with the atomic definition of the second. So let's finish with a few comments about the second. Firstly, I want to say, I referred earlier to the fact that the General Conference in November did touch upon matters of timekeeping. And the reason for that was that UTC and TAI have never been defined formally within our system, defined by our member states or addressed with the authority even of the CIPM. So resolution 2 of the 26th meeting confirmed, because this isn't new science, just confirming that the member states recognised that the definitions of TAI and UTC would be, as I hope we think they are. Now, the work within our system on time and frequency, of course, is coordinated by the CCTF, Consultative Committee for Time and Frequency, who maintain the list of recommended values for frequency standards and wavelength standards. And of course, it's absolutely clear in the CCTF that there are many, many more clocks, and there are more clocks performing better than there were. So where next? Well, in 2016, the CCTF came up with its first proposal for a roadmap to move towards a new definition of the second. And in this roadmap, which definitely looks like the sort of roadmap that's put together by physicists, because it's a roadmap that only includes equations, although there is a time scale at the bottom. So in this roadmap of equations, the proposal is that in order to move to a new definition of the second, one would need 3 different optical clocks, either in different labs or of different species, performing at the 10 to the 18 level. 3 independent comparisons of clocks at 5 parts in 10 to the 18. Those could be transported or by some other advanced link. 3 independent measurements against 3 independent primary cesium clocks at 3 parts in 10 to the 16. Making contributions regularly to the calculation of TAI, and frequency ratios being measured between at least 5 optical frequency standards, each measured at least twice by independent laboratories. So that was the proposal in 2016. I think much has moved in just 3 years since then. Next year in 2020, the CCTF will meet again under the presidency of Noel Demark, recently elected to be the new president of the CCTF. He's deputy director of the Observatoire of Côte d'Azur and brings a great deal of experience to leading the CCTF in succession to Luc Erard. So as I summarise, the new definitions that I've talked about use what we like to call the rules of nature to create the rules of measurement. We're not constrained to specific implementations or to specific artifacts. They will tie measurements at the atomic and quantum scales to those at the macroscopic scale. But I'm afraid when one does experiments at the macroscopic level, one gets drawn back into needing mechanical experiments again. The new definitions will provide long-term stability. The realization of the units will be possible by new methods, and perhaps this is our biggest hope, that we are now open to new methods that perhaps have not yet been conceived. The challenge in the future will be to maintain comparability between these primary realizations. And I would say that this is the same challenge that we've had with all of our other measurement units and that the field of measurement science has been mainly concerned with for at least 100 years. There's still more to do. I've said a little bit about the optical second. There's a roadmap in place. It's the first version of the roadmap, and I hope that the CCTF, when they come together next year, will produce a refined and more detailed roadmap for the benefit of everybody working in this field towards this goal. So what I talked about was the effort of very many people, with 59 nations in the end voting to adopt this thing. At a time when there are very few global news stories where 59 nations agree unanimously, we were delighted to be the subject of world news. And we were delighted also to take the opportunity, courtesy of some colleagues at NIST, to put together this small video to celebrate the moment.
And the agreement from the world's scientific community. At times, it seems impossible. Accurate, precise measurements, and deliberate. But we did it. Je l'ai bien fatta. Il va nous échapper. Le voyage. Mais c'est roulé. Lors de toi.
So if you want to see any more of that, please take a look at our BIPM YouTube page. Thank you very much.
So thank you very much. And, well, I want to ask if there are any questions for Dr. Milton. Okay, John, microphone over there. Is there a microphone? If not,
I can speak loudly. So my question is, you mentioned that there are 7 base SI units. Set of physical phenomena. So I'm curious about whether the 7 units that are chosen have some relation to the set of phenomena that we're trying to describe, or is that a natural number for the number of these units, or is it completely arbitrary?
Well, this is a subject
We have 7, and we can knock one off quickly, because one, the candida, is associated with human response. Now, I think there is scope for a whole set of units that link to human response, and that we should put them in a category of their own, which actually would reflect the very great interest we have now in human response to phenomena. So that takes us down to 6. Then you have 1, the Kelvin, which really introduces us to the world of thermodynamics. You only need the Kelvin if you think of temperature in terms of the concept of thermodynamics. Then you need an electrical unit, because although you can set mechanical power equal to electrical power, you do need a convention as to the relative strengths, if you like, of the electric and magnetic fields. So if you put the magnetic field, if you put the energy of a field equal to E dot B, you need to know how much of the energy is in E and how much is in B. So if you said we didn't need a convention for electricity, then you could take the ampere out. And then I think we've got down to mass, length and time. Is that right? Did I miss one out? Oh, the model. Yeah, okay, the model, that's it. A convention. If you didn't want to do chemistry with a convention on how many entities there were in 12 grams, then you could leave that out. So that now I've got you down to mass, length and time, which probably satisfies that deep physicist desire to have this fundamental set of systems. There's another way to do it, which I won't do, which links everything to types of energy. I'm personally less of an advocate for that.
Here.
Yeah, you mentioned that the artifact that defined the mass couldn't be the stability couldn't be monitored. Had that original artifact been made of a resonator material like quartz, it could have been a 1 kilogram quartz resonator, for example, that you could lock to a atomic clock and monitor the stability of that mass with parts in 10 to the 14th accuracy, which is the short-term stability of a state-of-the-art quartz resonator.
I don't know whether that locking gives you the mass or the dimensions of the oscillator, but setting that aside, we could monitor the status of the old artifact, because surface analysis techniques are supremely precise. And if one set up a system of taking witness pieces of the same material and analysing, you could do that. Would that solve the problem? Well, possibly. Was there a problem anyway? I'm not really sure, because we now know that platinum iridium is a superbly well-chosen system to do this piece of work with. So the work they did back in 1889 turned out to get the right answer as far as the system was concerned. Why was it people had concerns? Well, this is a question to which we will not fully know the answer. Personally, I think that experimental techniques in the middle of the last century weren't as good as they are now. And it's therefore, if one looks at the data, it's quite easy to project onto today's data mistakes, errors that were made in the middle of the 20th century. So to me, that doesn't mean that the kilogram has necessarily changed mass, the artifact, but I suspect that the experiments that were done with it in the middle of the 20th century weren't at the level that we would expect today. But this is fast talking. We now have a system that doesn't need that kind of fast talking.
Is there another question?
Hi, thank you. Very interesting talk. You showed a roadmap for the redefinition of the second. And, I'm wondering if I could perhaps dare you to look at a crystal ball and say a few words about at least perhaps how long it might take to really come up with a new definition of the second.
So I thought the question about the crystal oscillator was difficult enough, but this is more difficult. The crystal ball. So I don't have a crystal ball, but I'd leave your community to answer the question. If these are the 5 elements that you think are necessary to move forward, then when's the point when these 5 elements are determined? I don't know. But this community is the only place that can know that answer. I'm looking forward to a good discussion at the CCTF next year, and hopefully preparations in advance of that discussion so everybody knows the issues ahead of the meeting. Yes, are those the 5 criteria? How close is the world community to addressing any of those 5 criteria? I leave that over to your community.
So I have a question. I take the great opportunity to have your point of view that is really global. So we have this redefinition, then there is implementation, and there is also how to make people understand, and so the training of young guys and schools, how it is ongoing on the worldwide. So the implementation, I think it's not that simple. Is it going in the proper way from your point of view?
Well, we have a very broad scope at the BIPM, but I'm glad to say that school education around the world isn't part of our scope. But nevertheless, we do everything we can to help the member states and the NMIs work on this. I would suggest that, what is the message that we want to give to the greatest population who are willing to listen? I'd suggest that the message we want to give is we are a community that gives you measurements that are stable and comparable and repeatable globally. That's the first message we want to give. If people really push and say, well, how do you achieve that? Then we can start talking about fundamental constants. But I really think we want to focus on the achievements in the community in producing globally reliable, recognised and stable measurements. So what I'm saying is probably, I'm not sure we have to start explaining to school children under the age of 18 how to realise the kilogram with a Kibble balance. I think we need to stick to the old message. We're doing a good job. Yeah, there's some complicated science in here. And as students become cognizant of Maxwell's equations and quantum mechanics and so on, they can begin to understand this. But I don't think we necessarily have to start committing ourselves to explaining to young people how quantum mechanics works in order to... You don't need to understand quantum mechanics to use a mobile phone. It turns out. So let's stick to the message. We're doing a good job that's going to provide stable measurements around the world. And if people really want to come inside and understand what's in the box, we'll talk to them about the complexity.
Okay, let's thank the speaker again. And